fantastic, and I'd like to thank the organizers for putting up this very interesting school, at least so far, from what we can see. This tutorial will be on multi-level Monte Carlo, and we'll go through the basics, basic estimates, basic construction, and basic estimates of the multi-level Monte Carlo method. Of course, it has a relation with the multi-level stochastic approximation, multi-level stochastic collocation that Catherine presented in her course, but there are. I will try to highlight the links later in the course. At first sight, it might look a little bit different, because there are common ideas about it. Okay, so that's the plan for today. I'm not sure I will cover everything today, so we'll continue tomorrow eventually. Well, the setting is the setting of forward uncertainty quantification in the context of, let's say, heavy computational intensive models. So, for instance, PDEs with random coefficients or stochastic differential equations with the random noise. And the idea of exploiting multiple discretizations to accelerate the uncertainty quantification analysis. I will first go through the basic Monte Carlo approximation. I hope there will not be too much overlap with what Catherine presented. I wasn't here on Monday, so I don't know exactly how much Catherine has introduced, but I will just recall the basic estimates for the Monte Carlo approximation, because those will be needed for the multi-level one. And then I go through the multi-level construction and the error analysis, and in particular this the important complexity analysis to understand what is the actual gain that you can have using this multi-level construction with respect to a single level of construction. So this is just tutorial slide on the importance of uncertainty quantification in many different fields, subsurface flows. Rob has mentioned this problem yesterday, or fluid dynamics, where you have a lot of uncertainty in the geometry of the airfoil or the operating condition and so on. You can name many interesting problems where you would like to include uncertainty in some parameters of the model, either because you don't have a full knowledge of those parameters, or because there are intrinsic variability and fluctuations, and you want to describe those fluctuations by some random variables or random processes. So this first part is just to set the notation that I will use throughout the course. So I imagine to have a random differential equation, which I write in abstract form like this one. So L is some differential operator. Again, it could be a PDE, it could be a ordinary differential equation. U is the solution that I'm looking for, and F is the right-hand side, and Y is encodes all the randomness in the system. Again, it could be some parameters in the model that you don't know precisely and you want to model as random variables, or could be a stochastic process that describes maybe the permeability in a subsurface flow model, or maybe describes some random fluctuations in the right-hand side if you look at proper stochastic differential equations, and you have some rough force in turn acting on the right-hand side. So this is not really essential. I didn't want to be too heavy on the notation, so I suppose Y is a vector of random variables, but you think of this as a more general object, like a stochastic process or a Brownian motion or something like this. So the fact that here I write it as a vector of random variables is not essential, and actually this n could be infinity if you expand the random field in series. You will have an uncountable number of random variables describing the whole process. The underlying assumption is that this model is well posed, so no matter what realization, at least almost every realization of this random vector or random process, you have a unique solution of this equation. so is strong or important, strong existence, and the solution lives in some function space V, and I will mostly focus on the case of Hilbert space or separable Hilbert space, but I will discuss a little bit also on the case where V is not a Hilbert space, it's just a Banach space. And then this induces a mapping from Y to U, and I assume that this mapping is measurable with respect to the proper, let's say, Borel sigma algebras that you can define on the spaces, and has some integrability. This means that if you integrate this, the V norm of U to some power P, over the distribution of the random parameter Y, this quantity will be bounded for some P larger than 1. Mostly larger than 2, so I assume that I have at least second moments. But we also discuss the case where you don't have second moments, what you should expect. So the most classical case is where you have at least second moments and you are in a Hilbert space, and this is where you can have very easy and nice error estimates on the Monte Carlo, Multilevel Monte Carlo set. And there is another important assumption in this forward UQ framework is that the distribution of Y is known in advance, and we know how to sample from this distribution. So we can generate independent samples of Y, and then for each Y, conceptually, we can solve this equation and then the corresponding solution U, at least approximately. Which, of course, if you go into inverse problems, this will not be the case, and then you will have to devise some proper sampling strategies to sample from a complex posterior distribution. But for the time being, I assume that I can sample independently from the underlying distribution. And then what's the goal of the analysis? Well, the goal is to look at some output quantity, which I denote by Q. And this output quantity will typically be a function of the solution of the differential problem. So it's a Q tilde of U. So Q tilde takes an element in V and returns an object in some other space Z. And now you can think of Z as being just R, so you're looking at just a scalar quantity of interest, or you may look at a vector quantity of interest, so multiple scalar quantity of interest, so Z could be Rk, but Z could also be a function space. So you may look at a response that is a whole function, maybe U itself. Maybe your goal is to compute statistics of the solution directly, so as a function. Okay, so Z could be a function space. As I said, if you take just the identity here, this will be looking at the solution of the whole differential equation. Of course, I have to assume something on this function Q tilde. I don't want to go too much into trouble, so I assume that it is Lipschitz function. Okay, so if it is Lipschitz, it means that, okay, so this Q tilde acts on elements in V, so then I can look at the output random variable that is Q tilde of V of Y, so as a function of Y, so that's the quantity I want to approximate statistics of this quantity. And if I assume that Q tilde is Lipschitz, then Q as a random variable will have the same integrability as the solution U itself, so it will be like P, the same P, with values in this space Z. Okay. So, this is the output quantity of interest, and then I want to estimate statistics of this. The simplest one is just expected value, which will be an element of the space Z. So conceptually, it's the integral over all possible outcome. This is very nice, but sometimes it reacts a bit. Yeah, okay. So the integral over the distribution of Y, of Q of Y. So Q of Y is an element of Z, and then you integrate it, and you get an element of Z as well. You may look at the variance now. If you look at the function values, I define the variance in this way. So you take Q minus the mean, and I evaluate the Z norm square and the average this norm. You may look at the covariance. Again, if Z is a function space, you can look at this element in Z across Z, defined in this tensor product. If it is a vector of Z, if Y is a vector, this will be the usual covariance matrix. Or you can look at some other functionals, take some functional on Z and you look at some scalar value, or you apply Q and phi on Q. Okay, so that's the model, somehow the goal of the analysis. But now we have to realize that this model is a complex model. We cannot solve exactly the equation, so we have to use some numerical discretization. Again, it could be finite elements if it is a PDE. It could be some time integration if it is a ODE or a stochastic differential equation, and so on. So I denote by H the discretization. So H will be some discretization parameter. Again, it could be a spatial discretization or temporal discretization or some other discretization. And I denote by UH the solution, the discrete solution which satisfies an approximate problem of this type. Okay, and again, I have to assume something on my discretization, so I assume that it converges when H goes to 0 in some sense. So in this LPV sense, so let's say almost surely UH converges to U when you measure in the V norm, and actually the Pix moment converges as well. And again, the same on the output quantity, maybe with some better integrability, if Q is a nice function, or maybe not, it depends. Okay, so that was just to set the problem and the goal. And now, say, how do we approximate with respect to the randomness? Why? So in this course I discussed Monte Carlo type approximations, which I assume that all of you have seen or are rather familiar with, but will recall a little bit the theoretical results on this approach. So let's say that we look at a simple goal of computing the expected value of Q. Again, Q being this output function, output quantity, the scalar or vector of the function in some Hilbert space Z. And here what we discuss is specifically the Hilbert structure, which is rather important in the mean square analysis. So how does it work? Okay, I said I know how to generate IID realizations of this random variable Y, so I generate M replicas, independent and identically distributed, so this IID keyword. And then for each one of those, I solve my discrete problem, and I get the solution UHI. Given this, I compute the corresponding output QHI, and then I just estimate the expected value using the sample average of these evaluations. So very simple, very straightforward. So the final estimator is this mu hat H Monte Carlo. It's the sample average of the output quantities. So what can we say on the accuracy of this estimator here? Again, I think those are very, very standard calculations. So first, what is the, on average, the expected value of this estimator? So if you imagine to repeat the experiment many times, every time you draw random samples and you average. So on average, what you should get is the exact expected value of the approximate Q, the QH. Okay, this is just because of linearity of expectation. If I take expectation of the estimator, I can pass the expectation inside the sum, and each one of those are all IID because I have drawn IID samples. So each one of those has exactly this value, take this value mu h, so the exact expectation of QH, and I sum it n times and divide it by n, so I get mu h. Okay, just if you're not so familiar with Monte Carlo type analysis, one have to be a little careful on what this expectation means and what this expectation means. What this expectation means. Okay, so this expectation is just the integral of Q against rho. This expectation is the expectation with respect to the random sample here. So conceptually, this expectation lives in a much bigger probability space because I have my probability space is the n-fold tensorization of the underlying probability space, because now I work with the whole sample. So every time I run my experiment, I draw m random variables independent. So with a measure that is the product of rho n times. Okay. So I will write, I will not distinguish those two expectations, but keep in mind that this one and this one somehow different objects. Anyway, the whole point is that the expected value of the estimator is mu h, and mu h is not exactly the quantity I want to compute, which was mu, so the exact solution of my differential problem. So in this respect, I say that this estimator here is a biased estimator if I want to compute mu. It would be an unbiased estimator to compute mu h, but since my goal is not exactly mu h, it's mu, that's a biased estimator for the exact solution of the differential equation. Okay? So let me call B the bias. So the bias is the difference between the expected value of the estimator and the true value I want to compute. Okay, and I evaluate this bias, so I want to just a number, so I take this z norm of the difference. Okay, and now we know that this expected value is just mu h, so this bias is mu h minus mu. And this is purely dictated by the discretization that I have done on my differential equation. Okay, so there's no Monte Carlo anymore, there is no more sampling. I just estimate, just so this is just a comparison between Q of y minus QH of y integrated over all possible values of y, and then I take this norm outside of the integral. Okay, so now you know somehow what error you are committing when you approximate Q by QH because of your type of discretization. If you have somehow uniform estimates with respect to y, then you can estimate this corresponding bias. So typically, you expect this bias to behave with to decay or to be bounded by some constant times some power of h. If h is the mesh size, you will have some rate alpha of convergence. Okay. So that's the bias part. Then the second important quantity is the variance of the estimator, which is defined here. So now you know that the mean is not going converging to mu, is converging to mu h, and then we can actually estimate how fast the deviation of the estimator from the mean is decreasing if I increase the sample size. So I would like to estimate the variance of the estimator. So again, the variance is defined as the difference between the estimator minus its mean, evaluated in the z norm squared and the mu average. Okay, and somehow we want to quantify how this variance decays with respect to the sample size. So this will be controlled by the sampling part. Okay, that's a very, very standard calculation. I just wrote it on the slides in a general Hilbert norm to convince you that what you most likely have seen in basic statistics courses for real valued quantities does actually apply in general if you have the inner product structure. Okay, so the variance again is this object here. The estimator is 1 over m sum of QH y, and now I subtract the mean, mu h, so I can bring the mean inside the sum. So I can re-express this in terms of the q prime h variable, which is qh minus the mean. Okay, so this quantity here is exactly this quantity here. And again, I exploit the fact that Z is a Hilbert space, so this norm squared, I can write it as the inner product of the quantity with itself. Okay? And now I use the linearity of the inner product, so now I have a factor 1 over m squared that comes out, and then I have a sum here and a sum here, so I can pull out the two sums. So I have a double sum on two indices, I and j, expected value of the inner product of qh prime yi, qh prime yj. Okay? And then the trick is to separate the diagonal terms from the off-diagonal terms. So on one side I have the diagonal ones, and then I have all the other ones. And the key point here is that now q prime has zero mean, because I have subtracted the mean. Okay? So those two random variables are centered, and they are independent, because yi and yj are independent. And because of this, I can, and this is the only tricky point, which I want to convince yourself. So if those two are independent, I can actually bring this expected value inside. Inside the inner product. If you want to convince yourself that this is true, the idea is, as usual, to approximate these functions by simple functions, so some functions that are piecewise constant on the probability space, and then somehow you separate the space part from the randomness, and then you can apply, if you go through approximation by simple functions, you can prove this result here in the case of independent random variables. But since those are centered, each one of those two expectations is zero, so all the off-diagonal terms disappear. Okay? Whereas all the diagonal terms are all equal, again, because all these variables have the same distribution, and they are all equal to the variance of QH. And then I have to sum n times, and I divide it by m squared, and hopefully there is one over m that is left. Okay? And that's the key point. Okay. So at the end I get the variance of QH, which is a given quantity, divided by m. Okay? And dividing by m comes from the fact that I can throw away all the off-diagonal terms, so I only have the m diagonal ones, and I divide by m squared. Yeah, so that was the standard analysis of the Monte Carlo estimator. So we can put the two terms, the bias and the variance, together. So we can look at the mean square error. So now we just look directly at the difference between the estimator and the quantity we want to compute in mean square sense. So Z norm squared and the expectation. And again, if you are in a Hilbert setting, the mean square error has a natural decomposition into bias square plus variance. And this is a composition that you have surely seen between bias and variance for real value functions, thus holds in general for functions in the Hilbert space. And again, the calculation is very similar as before. So I look at this mean square error, I sum and subtract the mean of the estimator, which is not mu, and then I expand the square. So I don't use triangular inequalities or Cauchy-Schwarz and so on, I just expand the square. So I will have the first term that is mu hat h minus mu h. This is exactly the variance of the estimator. the second term, which is mu hat minus mu, norm z square. Now those are deterministic quantities. Those do not depend on the random samples. So this expectation just drops because it's an expectation of something that is constant with respect to the sample. And this gives exactly the bias square. So again, the expectation, just you can cancel it, and you get v square. And the cross product between those two, again, will be the z inner product between this difference and this difference. But the first one is 0 in expectation. The second one is just independent from the sample. And the first one is, has 0 mean. So you can pass the mean inside the inner product. At 0 mean, it drops. Okay? So the inner product is 0, so I'm left only with the first two, which is bias square plus variance. And now we know that the variance decays as 1 over m times some constant, which is the variance of QH. And the bias, we expect it to decay with some power of h. Okay, this is a bias square, so this is the square of the error. This is a mean square error, so this will decay as some h to the 2 alpha plus 1 over m. And here you have the two contributions, so the contribution from the discretization of your differential equation and the contribution from the Monte Carlo. Okay? So if you want to reduce this term, you have to act on h, so how you discretize your PD or a V. And if you want to reduce this term, you have to act on the sample size. Okay? Any questions, doubts so far? Okay, I will come later on the, let's say, the complexity analysis. I'm trying to balance those two error terms. Let me discuss very briefly some more practical aspects. So suppose now you want to use this estimator here to approximate mu at some given accuracy. So now you have to control these two error contributions. Okay. How do you do this? Well, the spatial part, this really depends on your discretization of the PD, but there you have all the tools from standard numerical analysis and approximation of differential equations. The only difference is that this term is integrated over all possible realizations, but if you know how to approximate well for each realization, your PD, then you can control somehow this error. So let's say either you go into a posteriori error estimations, like the ones that Catherine has discussed yesterday, and you try to control each the accuracy at which you compute each realization of your output quantity, or in the multi-level construction that I will discuss next, you play with different grids. So you solve the same problem on different discretizations, and then a very cheap or easy way to get an estimate of the error is try to do some extrapolation. So if you have computed already the same quantity on the mesh of size h and size 2h, you can try to extrapolate, by which is an extrapolation, a better quantity q star, and then you use q star minus qh as a surrogate for the error, and this gives a reasonable indication of the size of the discretization, and then you average this over all the realizations. Okay, so it's a typical way how you can control the discretization error in your approximation. And for the variance, well, the most straightforward way, we know that the variance of the estimator is from this formula, the variance of QH divided by M, so we can try to estimate the constant here, so the variance of QH, and then just use this formula. And for the variance of QH, one can use the typical ways to just use a sample variance estimator. So you have already run your M simulations, so you have already collected this output, these M outputs, and then you can use the same sample to estimate at the same time the mean and the variance of the output quantity. So you can just use here a sample variance estimator. Here I gave the version, the unbiased version of the estimator. It's not strictly needed because you just need to estimate the constant, but to use the unbiased one. So you can estimate this quantity and this give again an estimation for the bounds. And then you combine the two and you have, it's not a guaranteed upper bound, it's just an error indicator, but it gives some indication on the mean square. So this, it's a general, most typical way of trying to estimate this mean square error. Now, if you work with scalar output, real valued output, there are also other tools that you can use, in particular the central limit theorem, to give actually better or sharper error estimations in probabilistic sense. So the central limit theorem says that if you rescale this difference, so the estimator minus the true mean, you rescale it by the square root of the sample size. So if you don't rescale it, this difference is going to 0, so in the limit the distribution goes to a delta. But if you inflate this difference, so you multiply by square root of m, then this distribution is not going to a delta anymore, it's going to a Gaussian distribution. Okay? And then you can say, okay, since in the limit this quantity goes to a Gaussian distribution, you can build a confidence interval. So say with probability, let's say 1 minus delta. If I cut the mass delta over 2 here and delta over 2 here, with probability 1 minus delta, this difference, so this square root of m mu hat minus mu hat h minus mu h is in this interval here. Okay? So then you can give a probabilistic statement on the error. Well, first, okay, this is on the difference between mu hat and mu h. Now, we want to compare with the two unknown value mu. So here I can just use a triangular inequality. So compare, write it as a sum of this difference here plus the bias. And then this difference here with a certain probability, 1 minus delta, will be in an interval. So this quantity here will be in this interval between those two values, C delta and minus C delta. That's the quantile of the Gaussian distribution. Okay, this means that the difference will be, sorry, I forgot. Sorry. I should divide by the variance. So if I divide it by the variance, it goes to a standard normal. Okay, and then I can use the quantiles of the standard normal to give the precise bounds. So this quantity here will be in this interval plus minus C delta. Okay, so then this quantity will be in this upper bounded by this quantity with probability 1 minus delta. That's only an asymptotic analysis. It only holds when n is large. But in Monte Carlo, you usually use a fairly large sample because you want to compute at a certain accuracy your quantity. So you are often in the regime that is rather asymptotic. So the distribution of your estimator is often very close to a Gaussian. So that's a quite reliable estimator, unless you are in some pathological cases where either you use a very small m because maybe of computational resources, so each simulation takes days and then you can only afford 10 or 20 simulations, then you might question the use of central limit theorem, or because your output is particularly bad, so it's has particularly fat tails, and then maybe you have to be careful with the use of central limit. Okay. So again, you can come up with a probabilistic bound of this type, which looks very similar to the bound on the mean square error. The only difference is that here you put this quantile of the distribution, and then you can make this probabilistic statement that with probability 1 minus delta, you are in that you can upper bound the error of all realizations with this quantity. Okay, so then based on this one, this type of construction, so this was for the scalar case. If you are on the vector case, you can still use the central limit theorem and the vector version of the central limit theorem. It's a little bit more complex, because now if you want to estimate the norm or the squared norm of the difference, then you cannot use the quantile of the Gaussian, you have to use the quantile of the chi-square distribution, so sum of Gaussians, the sum of squares of Gaussians. In the infinite dimensional case, I haven't seen anyone using this, because then you have to use a functional central limit theorem. It becomes much more complex involved. But it would be interesting to see whether one can construct computable bounds based on this. Yeah, then I think I will skip to this part. That is just to say that then one can actually construct some adaptive Monte Carlo algorithms where you keep on refining H and increasing M until you fulfill a certain tolerance, prescribed tolerance. Okay? There are several ways you can do it. They are in general, again, not guaranteed as algorithms, but they work. I mean, if you want to make them guaranteed, you have to use guaranteed bounds, and that's pretty much more involved thing, and also they are super conservative as usual if you want guaranteed. Those ones are not guaranteed, but they usually work pretty well in practice. Okay, so let's keep this for nice. Okay, now this was the more practical part. Let's come back to the theory, and let's look at what is the complexity of the Monte Carlo algorithm. By complexity, I mean what is the work I have to invest to achieve a certain tolerance. For instance, if we look at the mean square error, which is this easy error way of controlling the error. Okay. So for this, let me make some assumptions, which you will have to verify for your specific problem. So as I said, suppose that if I look at the quantity I want to compute, so the expected value of Q, and I compare with the expected value of QH in the Z norm, this converges at a certain rate h to the power alpha. I compare if it is true. Now the other quantity that appears in the mean square error estimator is the variance of QH. Now, in principle, you expect QH to converge to the limit Q in L2 sense. So you expect the variance to converge as well. So you don't expect a priori big differences in variances, whether you compute it on the coarse level or on the fine level. So there might be differences, but asymptotically, this quantity should converge to a limit value. Okay? So let's suppose that all the variances could be upper bounded by a single constant, no matter what discretization you use. And the third assumption is that each evaluation costs something, and this cost increases when I decrease h. Again, reasonable, I have a final grid, I have to invest more time. So I suppose that the cost grows some h to the minus gamma. I put here a d just to remind that if you solve a d-dimensional problem and h is the mesh size, the number of degrees of freedom usually scales like h to the minus d. Okay, so h to the minus d is essentially the number of degrees of freedom in your discretization. And then you can assume that the cost is some power of the number of degrees of freedom. If you have an optimal solver, it will be just linear, so the cost is proportional to the number of degrees of freedom, so you will have gamma equal 1. If you have to solve a dense linear system, that's the worst case, to compute your U and your Q, then the cost may scale up to the third power of the number of degrees of freedom. Okay, so gamma could go up to 3 if you, for every evaluation, you have to solve a dense linear system and you cannot exploit the compression or some other tricks. Okay? And then you can have anything in between. If you have an iterative solver and you have a good preconditioner, you could have a gamma that is close to 1. So now we want to control the mean square error. So we want a mean square error that is, let's say, smaller or equal than some tolerance squared. So the most straightforward way is to split the error in two between the bias and the variance. So I assign tau square over 2 on the bias square. This means that this h to the 2 alpha should be smaller than tau square, so this fixes h as tau to the 1 over alpha up to constants. Okay. Same for the variance. The variance, I said, it's smaller than tau square over 2, but the variance was this variance of QH divided by m. Variance of QH is constant, so you just have to set m, which should scale as tau to the minus 2. Okay. So what's the overall cost? Asymptotic cost. Again, I'm forgetting all the constants. I'm just looking at how things depend on the tolerance that I want to achieve. So the cost of achieving a tolerance tau with my Monte Carlo estimator, I forgot an h here, sorry, it will be the unit cost of solving my underlying problem times the number of times I have to solve the problem, so it's CH times M. So now if I plug the formula for M, yes. CH is h to the minus d gamma, but h was tau to the 1 over alpha, so you plug everything in there, and then you get tau to the minus 2 minus d gamma over alpha. Okay? So tau to the minus 2 comes from the Monte Carlo part. Tau to the minus d gamma over alpha is essentially the cost of solving a single problem up to a tolerance tau. And you have the product of those two vectors, okay? Because you have to control both vectors. So remember this formula here will be quite crucial. So I anticipate already that the multi-level Monte Carlo aims at improving this complexity here. So it's not improving the rates. So it's not improving the 1 over m rate of Monte Carlo. What it's really trying to do is to reduce the cost to achieve a final tolerance tau. The idea is to reduce the cost. So if you want to achieve this tolerance, you need an h that scales like this. That's the finest h, the finest grid that you have to use to achieve this goal. But you can exploit coarser discretizations, hopefully to improve the performance of the method. Okay, so that's the whole idea of the multi-level Monte Carlo construction. Okay. So a couple of examples. Let's see how things scale in practice, this complexity. So let's take a stochastic differential equation that I've written here. And suppose that we just want to look at the solution at final time t, and we want to compute the expected value of the solution at final time. Okay, and we use the easiest discretization, which is the Euler-Mariano scheme, where we introduce time discretization, so uniform time step. And then you just use the order scheme, so that's the standard order scheme plus this number of fluctuations. So each time I have this b term multiplied by a Gaussian random variable, independent every time, that has mean 0 and variance delta t, which is the step size. Okay. Now, I'm not familiar with these schemes, just take for granted, and it is quite well known that if you estimate, if you look at the error in estimating the expected value of this solution at final time with respect to the time step h, this error behaves like h to the power 1. So this is a first order scheme in estimating the expected value. In general, in estimating the distribution of the function QH, This is called the weak rate. Weak because you are only looking at the distribution of Q. You don't ask necessarily that for each realization QH is close to Q. You just care that the distribution of QH is close to the distribution of Q. Okay? So this error in expectation decays at order 1, but then we need also the, okay, no. Just for you to know, if you were looking at the different pathwise, so for each realization, if I compare Q and QH, and I take, let's say, the L2 norm of this difference, this decays at lower rate, h to the power 1/2. So this is called the strong rate, okay, because it's a comparison pathwise of the realization of the process. Okay, so this other Majorana scheme has a strong rate 1/2 and weak rate 1. Okay. Now, for this analysis, we only care about the weak rate. In the multi-level, we will also care about the strong rate, but the strong rate doesn't appear in this mean-square error analysis for the standard Monte Carlo. So we have alpha equal 1, which is the power here. Dimension is 1, and the cost in this simple setting, if we suppose that evaluating these A and B terms is not costly, the cost is proportional to the number of time steps. Okay. So in this case, gamma is equal to 1, so the cost is just proportional to the number of evaluations. So if I plug those three numbers in the previous formula, we said D equal 1, gamma equal 1, alpha equal 1. So we have 2 minus 2 minus 1 minus 3. Okay? So the complexity here is tau to the minus 3. What does it mean? If I want to get one order of accuracy more, so if I want to divide the error by 10, I have to invest 1,000 more. Okay? So tau to the minus 3 is quite strong. Okay? Where does it come from? Once again, it comes from the tau to the minus 2 and the other parts. So already tau to the minus 2 is quite constraining. So again, if I only had the tau to the minus 2, that's Monte Carlo. So Monte Carlo is very costly. Why is very costly? Because the convergence is 1 over square root of m, essentially. So if you want to reduce the error by 10, you have to invest 100 times more. But now you have to invest 100 times more, but on top of this, for each realization, you have to divide by 10 the step size. So it costs, each one costs 10 times more, so at the end you can end up with 1,000. Okay? So this hopefully shows that you need to do something here to try to improve this complexity. Let's look at a PD example. The one I think has been discussed a few times in this school. So let's say a simple elliptic equation with a random coefficient or a random field in there, E of y. I assume that this coefficient is almost surely positive and bounded, and even almost surely Lipschitz continuous random field. And I look at some functional of the solution, some Q tilde of u, could be some average of the solution somewhere, or some average of the gradient. So suppose that I discretize by finite elements, my right-hand side is nice, my domain is nice, and I said the coefficient is almost surely Lipschitz continuous, so I should expect convergence of order 1 in the H1 norm for U, pathwise for every realization of Y. And if I look at Q, it depends on if Q is a smooth functional or not. So I might get something better than order 1. And so let's say in H1, I should get order 1. And if I look at Q, if Q is a nice, if Q is just Lipschitz I will get also order 1 in Q, but maybe Q has better regularity, and then I could go up to order 2 if, by using some one nature trick and exploiting a joint regularity. So what is the cost? Well, if I have to solve my PDE in dimension D, the cost will be h to the minus d gamma, gamma being the efficiency of the linear solver that I use to solve each PDE. Okay. Let's suppose that okay, my Q is not so regular, so I get rate 1 here. And I use an optimal solver, so gamma is equal to 1. And if I have a 3D problem, so then again the formula was called minus 2 minus d gamma over alpha. So I said alpha is 1, gamma is 1, d is 3. I get delta total minus 5. That's absolutely unbearable, okay, to get something accurate. Maybe things is slightly better. Maybe instead of alpha equal 1, I have alpha equal 2. I have this multifunctional. And then already you can get something slightly better. But in the PDE framework is even more important to use some acceleration techniques to reduce this overall complexity. Okay. So maybe we conclude this part of Monte Carlo for this first lecture, and I would like to discuss something you already have not aware of, or you have not seen somewhere else. Is how does this analysis extend if one is not in a Hilbert setting? So the mean square analysis that I showed, which is very easy and very clean, relies on this inner product structure, so the fact that you have a Hilbert space. But sometimes you need to do estimates in some Banach space, or you might want to estimate not the mean square error, so not the L2 moment, not the second moment, but some other moments of the solution. Okay. So today, what happens instead is Banach instead of being Hilbert, and we may want to estimate the error not in mean square sense, not in L2 sense, but with for some other Q different than 2. Okay. So it turns out that the results are very similar with constants that are difficult to estimate, but essentially you have the same type of structure of the error. But the theory is much more involved, and I will just try to give you a flavor of this. So just as an example, suppose you look at a P-Laplacian problem. So this is a nonlinear analytic equation where here the diffusion terms is proportional to some power of the gradient. And then if your f on the right-hand side has right regularity, the solution of this problem in general will be in the space W1P, in the Sobolev space W1P. So first derivative that are LP integrable, P being the exponent that appears in the equation. Okay? Which could be larger or smaller than 2, depending on what P you choose. And in general, if things are nicely set, so this is pathwise. For almost every y, you have this type of spatial regularity, and in general, you have all moments if f is bounded and a also is uniformly bounded. Okay, so U is in this space Ls in probability with values in this Banach space. So suppose you are interested in computing the expected value of U in this Banach space and control the error in that norm. So then you are in this Banach setting. So for this one needs a notion, and this notion is one of Rademacher type of a Banach space. It's some weird object, so it's a sort of probabilistic statement to quantify something of a Banach space that is just a standard function space. So the definition is the following. So again, Z is some Banach space. We say that has Rademacher type P, p being between 1 and 2. If so, I look at the main point is the following. Essentially, the main point is actually written. Okay, no, sorry, I'll come back later. I don't anticipate too much. So let's just look at the definition here. So I take a sequence of elements in Z, n elements in Z. No, those are deterministic objects, so there is no randomness. And I take a sequence of IID Bernoulli random variables that can take plus minus 1 with probability 1/2. So those are symmetric random variables, and just take plus and 1, minus 1. And then I look at sum of epsilon I xi, so linear combination of this xi with coefficients plus minus 1 random and IID. Okay? And then I look at z norm of the sum to the power p, so the LP norm, LPZ norm of the sum. And I try to check whether this quantity here can be bounded by just the sum of the xi little LP norm of this sum. Okay? So if this is true, so if there exists a constant so that I have this bound for any choice of n points in Z, then I say that the space has Rademacher type P. Okay? Now, if Z is Hilbert, if I take the term in the left, I can again use the trick that the norm square is the inner product of the quantity by itself. So I can expand the norm using the Hilbert, the inner product. Okay? But this is a finite sum, so I can bring the finite sum outside. And then, so those are just deterministic objects, inner product in Z, and those are my Bernoulli random variables, which are IID. So once again, the off-diagonal terms in the sum drop, because those have zero mean and they are independent, so you only have the diagonal terms. And those, the variance, the expected value of epsilon squared is just 1. So you get exactly the sum here. Okay? So in the Hilbert setting, this inequality always holds with a constant c equal 1. That's the ideal case. So every Hilbert space has a Rademacher type 2. But there are other spaces which don't. One spaces, for instance, if you take the LQ space on a given physical domain D, one can show, I believe this as an exercise, that the Rademacher type is the minimum between Q and 2. So Lebesgue spaces with more integrability than 2 have Rademacher type 2. Lebesgue spaces with less integrability than 2 has Rademacher type Q. Okay, so if you have less integrability than 2, you have a reduced Rademacher type. This for Lebesgue spaces, and is also true for Sobolev spaces if you look at derivatives. Last comments, if a space has Rademacher type P, has also Rademacher type Q smaller than P. So it's nestedness. So why is this relevant? Because of this important Marcinkiewicz-Zygmunt inequality. I give here a generalized version. The standard version is just with P with Q equal P. So if you take Q equal P, this says that the expected value of the sum of the yi to the power p can be bounded by some constant times the expected value of the sum of the yi to the power p. Okay, if q is equal to p, this is 1. Okay. This means here now I can bring the sum outside. Okay. So this is the typical. So this, sorry, I should have said what are the assumptions here in this inequality. Suppose you have a space with a Rademacher type P, somewhere between 1 and 2, and you look at a sequence of independent, not necessarily identically distributed, just independent random variables in this space LQZ, which are centered. Okay. Then, if you have, then you have this type of Marcinkiewicz-Zygmunt inequality. And if you look at this, it does generalize the case that you have in the setting that the variance of the sum of random variables is just the sum of the variances of the random variables. Okay, in standard mean square analysis, you say if my random variables are independent and centered, well, if they are independent, the variance of the sum is the sum of the variances. If they are centered, the expected value of the sum is the sum of the expected values, which is essentially what you get here up to a constant. Okay? So this Marcinkiewicz-Zygmunt inequality is a generalization essentially of this splitting here. Notice that if you just use triangular inequality here, okay, to pull out the sum, you would get a constant that blows up in M. That's the whole point. So you want to do better than the triangular inequality, because you don't want to have a constant that is blowing in M. And you want to improve with respect to triangular inequality by exploiting independence. But you don't have this Hilbert structure, so you cannot just expand the square and exploit independence explicitly. So you have to go through this proof of this Marcinkiewicz-Zygmunt inequality, which I don't have time to show. My plan was to do it, but it's a very nice trick that links to the definition of the Rademacher type. So the idea is to do a symmetrization of this random variable. So you create a copy of y, and then you look at y minus its copy, which has a symmetric distribution. And then you can do some conditioning, so in a sense you can replace y with the symmetric copy, and because of the symmetry now you can plug the epsilon, and this doesn't change the expectation, and then you can use this characterization and conclude. Okay? So this is the main tool that you can use in the Banach setting. How does it translate in practice? Well, no, it's this here, sorry. So with this, one can actually, using this Marcinkiewicz-Zygmunt inequality, one can actually show this bound on the LQ norm with value z between the estimator and the true expected value. Sorry, I messed up things. Okay, I have not put the h here. So if you put the h, you should compare the estimator with mu h, with the mean. And then you have here a bound that depends on this LQ norm of y minus the okay, sorry. This was still written in general terms. So you have a random variable z in LQ of z. You want to compute the mean, and you use a Monte Carlo estimator. So now the yi are IID. This estimator is unbiased for computing the mean of y. Okay, and then if I look at this error in the LQ sense with value in z, this decays as some constant divided by m to the beta, the constant being here the LQ norm of y minus mu, and beta is 1 minus the minimum between p and q. Okay, so So you may get a reduced convergence rate if either your Rademacher type is not 2, or you look at estimates in LQ with Q smaller than 2. So you don't have second moments on your quantity on which you're doing Monte Carlo. So if you don't have second moment, if you have fewer than second moments, you will have a reduced convergence. And if you don't have Rademacher type 2, you will also have a reduced convergence. Okay? Okay, skip the proof. You have the proof in the slides. You're welcome to read. It's just essentially a corollary of the marking shape inequality. Okay, now if we go back to our setting where we wanted to approximate some output Q by taking the expected value of QH, then we will have also the bias in the estimate. So here I can use again triangular inequality. So if I compare the estimator with the true value, I can sum and subtract the mu h quantity. So I can bound by the z norm of mu h minus mu plus this other part, and for this other part I use the previous result. Okay. So at the end you get this type of estimates. You generalize the mean square analysis in the Hilbert setting. So do you see this in practice? Ask Tommaso, he's now the expert on these things. So if you don't have enough second moments, yes, you see it very well, that you have a reduced Monte Carlo convergence. If you are on a weaker Banach space, you do actually see it, but somehow you have to find good examples that show this reduced convergence, because many times you can embed this bad Banach space in some other Hilbert space, and then you get the convergence of the Hilbert space. Okay, so here is an example. So we took this very bad function here. So y is a random variable. X is a spatial coordinate, so this solves, let's say this is a solution of this simple problem, minus u second equal f. So you set f so that this is the solution. And this has singularities on the second derivative at a random point, y. Okay? So it has singularity both in the physical space and in the random space because of this moving singularity. So then one can show that for any y, this solution is in W1P and is actually integrable in this space for any q, but you are limited by the low regularity in space. Indeed, if you run Monte Carlo, try to equilibrate the spatial error with the Monte Carlo error. If you just take the standard scale 10 to the minus 2 for the Monte Carlo, you don't actually match the target tolerance. So M in that case, like 10 to the minus 2, it's too aggressive. So you don't recover the right error. If you use the theory which would give this scaling of M with the tolerance because of the reduced Monte Carlo convergence, you do actually, so this is the pink one, which follows the blue, which is the target tolerance. So you see that you do recover this correct error for different Rademacher types. But then one could go to a much finer analysis and realize that since we are approximating the PBE, we are in finite dimensions, and every finite dimensional space is isomorphic to some Hilbert space. So in finite dimensions, you always have the good estimate. You can always use the good estimate. The problem is that the constant now may blow up with the h. But then you can check carefully how the constant blows up with h and do a finer balancing of the error, taking into account this blow up of the constant. And then you can come up with a better tolerance, so a better Monte Carlo that uses less samples than this one and still matches the error by this finer analysis discrete type of marker. Okay, sorry, I'm over time. Already the first lecture. So I'll stop here. I don't know, should we start 10 minutes later or I'll ask the organizers?